Okay, good morning, everyone. Let's get started with lecture 14. In this lecture, we're going to study speed and position control of DC motors. We're going to go one step beyond control systems and see how to integrate a DC motor with an H-bridge and a discrete controller such as Arduino, and how we can develop a PID controller, implement a PID controller in a Arduino, for example, or a discrete version of the PID controllers we covered in control systems. So this lecture is very useful for all of you that are implementing some sort of control in your design project. Most of you are. And I actually have seen many people that already implemented the concepts that you're going to see here, but let's cover them anyways, just to get these in our database. So today we're going to do speed and position control of DC motors, and in the next lecture, we're going to look at torque control, which is equally important for mechatronic design projects. By the end of this lecture, you should be able to implement a closed loop PID control for speed or position control of a DC motor and analyze the influence of motor parameters in the frequency response of DC motors. We're going to go back to control system and revisit some of the topics we addressed there, such as frequency response, Bode plots, and I'll see how the parameters of the DC motor will affect the frequency response of the motor itself. There are many applications of position control, position and speed control. Let me give you here one application. Let's consider, for example, that you have a robotic arm that operates, is powered by DC motors and operates on a patient. And here, in this example here, this robotic arm is operating on the eye. If you want to do some sort of control, position control, there is no room for overshoot. As you can see, if we want these needles to touch the eye and our controller has any overshoot, that means that the needles would first puncture the eye before they come back out and then they reach a steady state. This sort of oscillations, this sort of overshoot is not acceptable in this application. We need to determine the appropriate control gains or the appropriate control structure in a way that overshoot is never present in all operating conditions. Right. Another great question that we could ask here is how can we control these motors to achieve a precision that is in the micrometer range? I'll give you an example. I have two robotic arms in my lab. They are pretty much this tall. They look like toys, but they are industrial robotic arms, and they have an accuracy of 5 micrometers. It's micrometers. It's really precise. How can you control these motors one by one, combine 6 of them, and they still have an accuracy of 6 micrometers? Well, this relies on a perfect closed loop control for position or speed control. Here is a different application. We're not going to cover this in this lecture. We're going to cover that in the following lecture, but let's assume that you have this robotic hand here, this gripper, and this gripper is to be controlled to grasp some objects. We can do position control and just make sure that the gripper reaches a certain position, and hopefully that will be sufficient to grasp the object. But how can you make sure now that the force we are applying to this object is not too much and that it's not going to damage the object? We need some sort of feedback, and this wouldn't be necessarily a position control unless we have cameras that can track these objects, determine the shape of the objects, and then determine how much the gripper should move. Well, we can implement a control system like that. That would be indeed a position control, but that would rely on a strong imaging system that gives you the shape you're trying to grasp. Another option is to move away from position control and try to do force control. So we always apply a certain force that will ensure contact between the object and the robotic gripper, and then you develop your controller in a way that there is no overshoot. The force never exceeds a critical threshold, and in that way it will not damage the object. We are developing right now in the lab a system to image the lung with an ultrasound machine using a robotic arm. So the robotic arm holds the ultrasound probe and scans a lung simulator that is there, is breathing, is moving. And the idea is to ensure that the contact between the ultrasound probe and the lung is always at the same level. So if the lung moves up and down, the ultrasound probe will need to move up and down. And that will not need to translate along the lung to take these ultrasound images. How we make sure that this always gives good imaging quality? We need to make sure that the pressure between the ultrasound probe and the lung is always the same. So that also relies on an accurate control system. So if the pressure is too much, you basically move the probe a little bit back. If the pressure that is measured, the force between them is not high enough, then we move the ultrasound probe closer to the lung, and that is a dynamic system that moves, and then the ultrasound probe can be steered along the lung to create good images. That's another example of force control, and force and position control is a hybrid controller. So applications of force and position control are everywhere. And in your design project, it is very likely that you're doing some sort of position or speed control at this point. So let's get it started straight into it. This lecture is not very complicated. It's just a collection of different topics that we need to understand the behavior of the system in frequency response and the effect of a controller. But there is little new information here. So let's look back at lecture 13. We developed this model for the DC motor. We have two parts. We have the electrical part and the mechanical part. We developed two equations, one that balances the voltage in the electrical part, the other that balances torque in the mechanical part. And the link between these two parts is the back EMF generated as a result of rotor rotation in the stator, and the torque generated in the rotor as a result of the current flowing in the stator. The link between them is simply a proportionality constant that we derived in the last lecture, and we came to the conclusion that these two proportionality constants are the same. They depend on the motor parameters, how the motor is built, how many coils we have, how many turns we have, etc. And we also concluded that this back EMF is proportional to the speed of the motor. The faster it rotates, the more back EMF is generated in the armature, the more back EMF opposes current in the armature that comes from the voltage source. We've also concluded that the torque, on the other hand, is proportional to the current itself. The greater the current, the greater the torque developed in the motor. The greater the torque generated by the electrical part is to the motor, and greater the acceleration if no torque opposes that one. And these two equations are summarized here. We had one for the electrical part, one for the mechanical part. You recognize all these terms. Here is one of those constants that I mentioned, the constant, the speed constant, and the other constant would appear here, where the torque developed by the motor is simply that same constant, but let's call that a Ki here, just to avoid confusion, times the current in the motor itself. And that's the torque developed in the motor. So the first equation is the sum of voltages in the stator, in the circuit, and the second equation is the sum of torques applied to the rotor. We then isolated the voltage, we isolated the current and the speed into equations like that, and that's where we stopped in the last lecture. So these two equations now give the current and they give the speed for certain parameters, such as the input voltage, the motor parameters itself, and the disturbance torque TD. It's an external torque being applied to the motor, which will, of course, influence the speed of the motor itself. Now, for the analysis that follow, we are going to consider the motor to be rotating in a steady state. If that is the case, which of these parameters will have no influence on the steady state response? Let's say the steady state current and the steady state speed. Which of these parameters can be neglected? I cannot see the chat, so if you can speak on the mic, that would be great. Nobody?
What is the difference between the KE in the circuit and KM in the first line?
So KE gives the relation between the torque and the current. Km gives the relation between the back EMF and the speed. Ki, according to our last lecture, and Km are the same value.
Okay, thank you.
Okay, so let me repeat my question. If you want to use this system in the steady state, which of these parameters does not influence the steady state response for speed, for position, sorry, for current and voltage, and for current and speed, sorry.
So the inductance, sir?
The inductance, very good. The inductance does not influence the steady state current, only influences the transient, so that term can be neglected. What else can be neglected? The inertia of the motor. Right? In the same way that the inductance only affects the transient current, the inertia only affects the transient speed. And that can be also neglected. So these two terms, these two S's, can now go to 0. In fact, if you had more S's, we could set them all to 0. But if you're interested in the steady state response, that is the steady state current, the steady state speed, once the motor settles at a given operating point, then the inductance and the inertia have no effect. So they can be neglected. And if that is the case, then under steady state conditions, these two equations simplify to the following two. Now we see that only parameters affecting the steady state is the resistance. That makes sense. The greater the resistance, the greater the current, the smaller the current. And viscous friction, the greater viscous friction is, the smaller the maximum speed of the motor is. That makes perfect sense. Now let's take these two equations one step further, and let's create two independent equations without the current. The current being an internal variable in our system, we don't want the current to be there. So let's create two equations that will give the speed and the torque developed in the motor as a function of the other parameters. So to find the equation for speed, for example, we can take this first equation here for the current, replace the current right here, and solve for the speed, which will give this equation for the speed. We can do the same for the torque. This would be the torque developed in the motor, current times Ki. We can now take the speed and replace the speed there, and then solve for torque itself. And then that gives the second equation. And let's assume that these two equations represent the steady state speed and the steady state torque. In other words, the steady state current divided by the torque constant when the motor is driven at a constant voltage V. Okay, so these are the steady state speed, the speed the motor reaches when we apply a voltage V, and the torque it develops when we apply a voltage V, and it rotates at a speed omega. Now let's plot these two equations. Let's plot the torque, let's plot the speed, and let's plot as a function of different voltages. Let's start with the graph on the left. So here we have a torque speed graph for different levels of voltage. So the voltage is increasing this way. And the voltage is increasing that way, and we take the speed here, we take the torque for that axis, and our input is V, the applied voltage. All other parameters are assumed to be known. What can we conclude here? Let's look at one case. Let's take V equals to 10 volts. That is the top line going down. We can see a linear relationship between the torque and the speed. A linear relationship between torque and speed. If torque increases, the speed decreases. If the speed decreases, torque increases. Why? How can we explain that? Does that make sense at all?
Does it have to do with the fact that when torque is proportional to current, but speed is proportional to the voltage, and when the current's going up, the voltage is going down? Something like that? Something
like that. Yes. Let me rephrase your statement as follows. The greater the speed, the greater the back EMF, the smaller the current. The current in steady state will be the input voltage minus the back EMF divided by the resistance. The back EMF is a function of the speed, which we can say it's simply K times omega. I is the torque is proportional to I. So the greater the current, the greater the torque. So let's look at this equation. The greater omega, the greater the speed, the smaller the difference between V and the back EMF, and then less current is developed in the armature, and the torque decreases. The torque decreases, right? Which is exactly what it just said, just in a different way. So that as the torque increases, the speed decreases, the speed increases, the torque decreases. And that's the relation we have. Now let's further analyze this graph here. We have a region where the speed is 0 and the torque is very high. What is the torque called at that specific line there? That is?
Stall torque.
Exactly, the stall torque, or the torque at no speed, the torque at no EMF. And when the EMF is 0, then you have the current as V over R, right? Because the back EMF is 0. And this torque is called the stall torque. There is no speed, but this torque generates or requires a very, very high current, which is not the nominal current. And it can only be sustained for some a fraction of milliseconds or some milliseconds. Beyond that, the motor is certainly not designed to sustain that torque, and the coils will heat up and probably eventually burn. So this torque cannot be sustained. That is to say that there are some operating ranges in this motor that the motor is designed to operate at, and there are some other ranges where the motor is not designed to operate at. If we now take torque and speed, multiply them, and create the mechanical power, and we plot that as a function of speed for different voltages, so each of these lines here is a voltage, this is what we see. And when you buy a motor, this is the sort of specifications that we'll see in the data sheet. It's these two curves, and we'll come with extra information saying that, for example, I'm just a guess, this is the range, the nominal range of the motor. This is the range where the motor should be operating. And the data sheet, if you're buying a good motor, will further state that there is another range here that it can be used for a certain amount of time, but it's not the nominal operating range. Right? So these are the specifications that will come in a data sheet. Now let's analyze two specific cases. The first one, let's suppose that the system is operating in steady state with a certain speed, a certain voltage. There is no load, so TD equals to 0, and there is no friction. There is no load and there is no friction. What is the current flowing in the motor? And what is the torque developed in the motor? Any ideas? Let me put it this way. Let me ask you the question in a different way. If there is no friction, if there is no load, what is opposing the torque developed by the motor? Nothing. Nothing is opposing torque developed by the motor. If the motor is then assumed to be in a steady state, what torque can the motor be providing? Zero. Zero torque, because there is nothing to overcome. There is no friction. There is no load. If the motor is in a steady state, is rotating at a given speed, that from the equation above, we can see that it will simplify to this. V divided by the time, the speed constant. Then we can say that because there is no torque to overcome and the system is at a constant speed, which means acceleration is 0, the sum of all torques must also be 0, and that is to say that the motor develops no torque. So if the motor develops no torque, what is the current in the motor?
Is it 0?
It's also 0. It's also 0. How can you get a current that is 0? Well, the current will come from the equation we just had. That is the input voltage minus the back EMF divided by R. The only way to get this to 0 is to have V equals to E. So in this case, the back EMF balances the applied voltage resulting in zero current, resulting in zero torque, because there is no torque to overcome, right? So don't try to make much physical sense of this, because in reality, there is always friction. There might be a load torque, but friction is always present in the system, right? But in this hypothetical scenario, if there is no torque to overcome, then there is no torque developed by the motor. This is just to introduce the next slide you're going to see now. Now let's go to a more realistic case. I don't know if I updated the copy you have. Now there is a no here that you can remove. There is friction, so that in O there, just neglect it. And let's assume a more realistic scenario where we have now a load torque and we also have friction. They're both different than zero. What is the torque developed by the motor? Let's say that we only have friction. The load torque is zero. So what would be the torque developed by the motor in a steady state? What is that torque doing in the motor? It is overcoming friction. If there is friction and the motor rotates at a steady state speed omega, the torque the motor is developing is omega times B. That's the viscous friction in the motor shaft. That is the viscous friction in the motor shaft. If there is friction, there is a torque that opposes motion, but because this is moving at a steady state speed, then the motor must be providing the same amount of torque to counteract the effect of friction. And that is given by omega times the coefficient of viscous friction B. What is the current? Is there a current? Well, if there is a torque, there is a current. And what is the current? The current is simply the torque divided by the torque constant. So that is the current in case of friction, right? And this current is the current when, let's say, we turn the motor on. When you turn it on with no load, you will notice that the motor is spinning at a maximum speed, and there is current developed. That current is overcoming friction generated by the shaft, right? And that's what we would call the no load speed and no load current. If there is a current, then that is to say that this equation here is no longer zero, which means that the back EMF no longer balances the applied voltage. The applied voltage is greater than the back EMF, is slightly greater, and that gives now a discrepancy there that generates 1 divided by R, the current in the motor. If we now have a load torque as well, so we have friction plus a load torque, what is the current doing? Oh, the current is supplying enough torque to the motor to overcome both, to overcome the effect of the load, the external torque being applied to the motor, and to overcome friction as well. So speed and torque depend on the load and depend on friction, right? If you apply a load against motion, of course, the speed decreases. The current now needs to increase to overcome that torque. If the torque is applied in the same direction of motion, then it's the other way around. The speed will increase. Friction is always present, and the load is unknown, as we cannot model the load. So this analysis is to say, what limits the maximum no load speed in a DC motor? What limits the maximum no load speed in a DC motor? What parameter? What parameter limits the maximum speed or the no load speed in a DC motor? That's the coefficient of viscous friction. Exactly, yeah. The coefficient of viscous friction now limits the maximum speed and no load. Okay, before we go into position and speed control, are there any questions?
Can you just explain that last part again? What you just said about the viscous friction thing?
Yeah, which part exactly?
Like how that's the only thing that affects it for voltage? Oh, for speed, sorry.
For speed, well, the only thing that affects the limiting factor for the maximum steady state speed is the coefficient of viscous friction, because the only torque developed in the absence of a load is the speed times the coefficient of viscous friction. Right, that's the only thing that opposes motion. So if the motor is applying a torque T, right, the overall torque in the motor is T minus B omega. Right, this is equal to J omega dot. Right. So if you calculate the maximum speed, you can solve this differential equation, and you can and you will see that this will be inversely proportional to, if you take the limit of this equation, inversely proportional to the coefficient of viscous friction. That makes sense. The more friction there is, the lower the maximum speed. Right? But
Okay,
there is nothing
thank you.
else. There is nothing else applying a torque against motion. That's the only. That would be the only element in the absence of a load. Anything else? Any other questions? No? All right, so let's move on to transfer functions. The transfer functions you're all familiar with. So we're going to study the speed response of a DC motor. So for that, we need to characterize the motor, and we start with the transfer functions. So here is a block diagram of the motor. We also developed this in lecture 13. We have all the elements here. We have the circuit, we have the mechanical part, the two constants, the load torque right there, and the speed and position of the rotor. Position is the integral of the speed. Let's start with the speed transfer functions. If you are interested in the relation between the speed and the input voltage, we can simply set the disturbance torque to 0, calculate the closed loop equation here, transfer function, and that gives equation 1. This is from control systems. You should all be familiar with this at this point. So I'm going to skip the derivation here because I think at this point it is indeed very trivial. So that's the speed to voltage transfer function. We see what you see here. The speed to voltage transfer function has two cutoff frequencies, one that it will be dependent on the electrical part of the system, the other that it will be dependent on the mechanical characteristics of the system. That makes sense. If you want to develop a speed through voltage, first we need to develop a current, that is a torque, and that relation there is subjected to the response time of the coil, hence the first cutoff frequency that relates to the electrical part. Once we have developed this current, to go from current to torque, that's just a proportionality constant. From torque to speed, now we need to overcome the effects of inertia and friction, hence the second cutoff frequency. From now, if we go all the way from voltage to speed, we need to overcome this through these two cutoff frequencies, one for the electrical part, one for the mechanical part. Now let's take the integral of this. If you want position, we simply multiply this transfer function by 1 over s, and then we get the position transfer function, again under the assumption that the load torque is 0. It's the same transfer function, but then we have this little s integrating the previous equation, and this would be the position to voltage transfer function. Nothing new here. Our system has two inputs, so to find the total output, we need to use the principle of superposition. Set one of the inputs to 0 and use the other one only. Find these two independent transfer functions, add them up. So now let's move on to the load torque. We set the voltage to 0, and let's see the effects of the load torque on the speed. To do that, we can rearrange this block diagram. Just set the voltage here to 0. This becomes our input, and then we just rearrange the block diagram in this manner. And now we can calculate the closed loop transfer function, whose derivation I'm going to skip because once again, this should be very fresh, just to control systems. And if you do all the analysis, we will end up with equation 3, the effect of the load torque on the speed of the motor. If we are dealing with a steady state, then all these transients can be set to 0. And this simplifies to this simple equation here. Okay, now let's put all these functions together. So let's do the superposition for the speed first. We have two inputs. We have the voltage itself when the load torque is 0, and we have the effect of the load torque When the voltage is 0, these are the effects on the speed. So here we have these two transfer functions. Now let's take a closer look at these two transfer functions 5 and 6. Do you see anything similar between them?
The denominators are the same?
The denominator is exactly the same. What is the difference? The difference is that this transfer function here is multiplied by Ls plus R. What can we conclude from this? Is multiplied by Ls plus R. Does this make sense? So one is the speed to position. Sorry, one is voltage to speed. The other one is torque to speed. And torque to speed is multiplied by Ls plus R. So if you take this second transfer function and multiply this by 1 over Ls plus R, we end up with that one. What does this mean? This means that if you pass the second transfer function, the torque transfer function, through some sort of low pass filter, we get speed. Does it make sense? Well, it makes perfect sense. It makes perfect sense because to go from speed to voltage, we have to overcome two cutoff frequencies. We have to overcome the electrical cutoff frequency. We need to overcome the mechanical cutoff frequency. If you now go from torque to speed directly, then the electrical transfer function, the electrical cutoff frequency should play no role because you are already applying a torque. And here we have now the electrical part showing up. So if you now multiply this by 1 over Ls plus R to get rid of that, we pass the torque through the low pass filter, we go to the first transfer function, which is speed, voltage to speed. Now, just an interesting observation that we can make by looking at these two equations.
Question.
One is the speed to voltage, one is the speed to torque. What is the final speed? Well, we can simply add them up. Now we have two expressions. It's the principle of superposition. The system is assumed to be linear. So we add them up and you get the total response for the speed as the sum of the effects of voltage and the sum of the effects of load torque. Okay. If you now want to do position, well, just integrate everything. Integrate the first two equations and integrate the overall equation into superposition form. And then it's the same equation we had before. The only difference is that everything is multiplied by 1 over S. Okay, that's the final transfer function for the system. Now let's look at a frequency response. Before we look at frequency response, why do we care about frequency response when you design something? What is the actual meaning of frequency response and what information can you take from this Bode plot?
You can find out what the actual transfer function is based on the different places where there's the, you know, the rises and falls and such, and the phase shifts and stuff.
Exactly. That's one application. We can indeed infer the transfer function parameters and the shape of the transfer function itself by looking at where the cutoff frequencies are. That's one application. We can also look at the phase shift between the input and the output. What else can we conclude from a design perspective there than a analysis perspective? What can we see here? We can tell at which frequency the motor will operate at. Which frequency the motor operates at. Let's say we want the motor to switch directions every 10 seconds or every 10 seconds. Then it would be a very low frequency, and clearly here the gain at low frequencies is relatively high, so it would have no problem. Excuse me. As you now start to increase the frequency, and let's say we want the motor to switch positions every 100 milliseconds, then the effect of load inductance and the effect of the inductance and the effect of inertia will be seen. because the current will take time to develop, the speed will take time to develop as a function of torque. And now these two cutoff frequencies don't let the system develop enough speed and enough current to provide sufficient torque as the frequency increases. So as we move on in frequency, we'll see now that to operate at the same level we had before, because the gain decreases, we'll need to increase the magnitude of the input voltage. So this block diagram, this Bode plot, in addition to telling you where these poles and zeros are and being an interesting tool to find the transfer function, will also tell you at which point you can operate your system. To, let's say, have a meaningful output at this frequency here, the only way is to bump up the entire input voltage, so the Bode plot would shift up and ensure a relation, a gain between, let's say, speed and position that is still sufficiently large to provide a given output. If you go very high in frequency, let's take this one for example, it would tell you that at that frequency, if you apply 1 volt at, let's say, 10 to the power of 5 radians per second, that gain is so small that the displacement that you get in that will be pretty much simply a vibration, or it will be pretty much no torque. So that information is all here in the Bode plot. Here we have two curves, one for speed, one for position. Which one is the speed, which one is position?
The red one position and the blue speed.
Blue is the speed and red is position. How can we tell?
Because at high frequencies, the motor doesn't move much.
That would apply to both. That would apply to both. Right? But how can we tell that one is position, one is speed?
The transfer function for position has an S on the bottom, so it's got a phase shift 90 degrees down.
Yeah, that's one indication. Very good. Because you have a pole at the origin, it starts at a negative 90 degrees, which is to say that you see that originally here we have a slope of negative 20 dB. Right, negative 20 dB, which is from the same effect. We can also tell this because this is flat. What does this mean? Well, it means that if you, let's say, we start giving the motor 1 second to rotate, and we look at the maximum speed, then you divide the maximum speed by the input voltage. We take 20 log of that and put it here. It's a flat curve. Does that make sense? Well, it makes perfect sense, because if we lower the frequency, we are giving more and more time to the motor for the motor to spin in one direction, reach a steady state, and then reverse direction and go to the other direction and reach steady state again. The maximum steady state, the more time we give to it, if you're looking at maximum position, it doesn't change. It's always the maximum speed. If you give 1 second, it will reach, let's say, 1 radians per second. You give it 10 seconds, it will also reach 1 radians per second. So the gain as you decrease the frequency is the same, and hence that flat line. That doesn't happen for position, because the more time we give for the motor to spin, the position will keep increasing. We give the motor 1 second, it will reach, let's say, 360 degrees. If you give it 2 seconds, it will go to 720 degrees, and so on. When you now divide these numbers by the input voltage, which is assumed to be the same, this ratio increases, and hence we see that as we decrease the frequency, the position gain keeps increasing. So that's another indication that that is the position transfer function. Now let's look at the speed transfer function. So we take this parameter here, the blue one, which is in here, the black curve. And now let's take individual parameters in this system and multiply them by 20 and then plot them here. So if you look, for example, at the stop curve here, this is when you multiply Ki by a factor of 20. The original curve is the black curve. When you multiply that by, if we increase the torque constant, we see that a Ki now increases by a factor of 20. And what happens? The gain overall improves. That makes sense. If Ki increases, the more torque is developed in the motor for a given voltage, so the gain goes up. And we can see the effects of all other parameters as well. We'll see, for example, that inertia multiplied by 20, which is the orange curve, will shift the cutoff frequency to the right, meaning that now the effects of the effect of inertia will start to take effect earlier in frequency, and so on. We can also look at the resistance. If you increase the resistance, the gain decreases, and you can look at how all other parameters affect the system itself. An interesting one to observe here: if you increase only Km, the gain decreases. The gain decreases because you generate more back EMF and less torque. Right? So the speed will also decrease. So all the information is there, and it gives you an idea of how each parameter in the motor will influence the steady state, or the frequency response, and eventually the steady state speed. This is to say that if you want a good motor, what should we see in a good motor? We should see low values for R, low values for L, high values for Ki, low values for that, low values for B. We should try to maximize Ki. Okay, unfortunately, Ki and Km are connected, so that's not really an option. Now let's look at the position transfer function. The position Bode plot. Do the same analysis, and you can conclude pretty much the same thing. Some parameters that decrease the gain are to be minimized. Parameters that increase the gain are to be maximized when you try to design the motor, and when you try to choose one as well. All right, so are there any questions so far before we move on to now feedback control? No? There isn't really much new information here. The only, pretty much the first slides are the new ones. This is just an application of Bode plots to the case of DC motor. All right, so if there are no questions, I will continue. Let's look now at a speed control. For speed control, we need to close the loop. So first we need to take the motor itself and use that as a plant. So this entire block diagram here becomes, this one here, becomes the motor transfer function. This would be the M of S function that are going to use that there. So input is V. It goes through all these feedback loops. So this is part of the motor. It's not part of the controller. It cannot be changed. It's what the motor is. It's how the plant is represented. This will result in this one of these transfer functions depending on where we go, if we go to position or speed. So you take this entire block diagram there, and that represents the motor transfer function in here. Input is the voltage, output is the speed. Now let's control that speed. If we are to control the speed, then what should you do? Well, measure the speed, create an error, transfer an error here compared to the desired speed, send that to the controller whose transfer function is C of S. The output of the controller now will take the form of two signals. The first one is a duty cycle. The second one is the direction of motion. The duty cycle is a number that goes from 0 to 1, hence it cannot carry the directional information. We need a second signal that now looks at the sign of the error or the sign in the output of the controller, and then determines if that duty cycle will generate a voltage going, making the rotor rotate clockwise or counterclockwise. That is given to the H bridge, and then the H bridge is the one that applies voltage to the motor. In control system, this block was not here. We are going from controller to voltage directly. Now in this course, we need to account for the H bridge itself. The input to the H bridge, again, is the duty cycle, goes from 0 to 1, and is the direction that determines which leg, which pair of the H bridge is delivering voltage based on the sign of the controller output. For the H bridge, we can make an assumption. We can say that the H bridge is modeled as a low pass filter and has a cutoff frequency that is much greater than that of the motor, or a much smaller time response than the dynamics of the motor. If you're using a PID controller, here is the form of our controller: KD, derivative gain, K, so it should be KP, proportional gain, KD, derivative gain, and KI, integral gain. And this now goes in the controller. So now let's see how this will affect the speed transfer function. And now we go from an open loop to a closed loop transfer function. Here is what we get. So the black curve is the same one we had before for speed. It's the open loop response. There is no controller. It's the open loop response of the motor. The blue one is now the one that closes the loop, is a new transfer function with the controller, and for now, just a proportional controller. What can we conclude? If you do speed control with a proportional controller, the gain is improved. Good news. The gain is improved, well, if k is greater than 0. What else can we conclude? Here is the root locus of this system, and that's the Nyquist plot of the corresponding closed loop system. What can we conclude from these two diagrams? What can you conclude in terms of overshoot and stability based on root locus and on the Nyquist plot?
It's stable for all values of gain.
It is stable for all positive values of Kp. Very good. Is stable. How can you tell? Well, the root locus never crosses into the unstable region. The Nyquist diagram never encircles -1. If we increase the gain, the Nyquist diagram expands to the right. What else can we conclude from this analysis? We can conclude that as we increase the gain, the system is never unstable, but overshoot may arise. Because now we broke away from the real axis. So with a proportional controller for speed control, the system is stable, provided that we are dealing with positive numbers for the control gain. At a certain threshold, the system will start to have some oscillations. Let's look at a speed controller with a PD controller. Now look at what happened to the gain. The gain now is a flat, more or less a flat curve. What happens there? Well, if we have a proportional derivative controller, our controller is adding a 0 like that. Let's call this S plus C1, is adding a 0 to the system. And by adding a 0, we improve the time response, because now we have basically all a flat line here. All right, so the frequency response is much improved. And look at the root locus. What can we conclude from the root locus?
0 overshoot.
0 overshoot, very good, for all values of K, all values of KD. So this is KP, KD, oh, that's correct, okay. And what else can you conclude? The system is always stable. So for speed control with a PD controller, everything looks pretty much, looks good. The derivative gain eliminates overshoot that we saw here. Makes sense. Now let's do a PID controller. Let's look at the effects of the integral gain. We see that the closed and open loop is only affected at low speeds. What else can we conclude based on the root locus and that we see here? What are the effects of the integral gain based on this root locus?
Sorry, question.
Yeah.
This is PI, not full PID, right?
If KD is set to 0, then it would be a PI. Yeah.
Okay, thank you.
Yeah. Well, let's focus on the effect of the integral gain. I think that's what I want to take. Yeah, it's kind of a bit misleading to call it a PID when KD is set to 0. It's more a PI indeed. So what are the effects of the integral controller based on these two graphs? Let's talk about stability. Is the system always stable?
Not for high values of k.
Not for high values of k. Very good. For high values of k, we are crossing into the unstable region there. All right, so high values of the integral gain may make the system unstable. certain values of k will also make overshoot appear in the time response, right? Because now the roots are complex conjugates.
I have a question.
Yep.
If that's the case, why would we ever need to use an integral controller?
Good
What's the
question. Why
purpose?
would we ever need to use an integral controller? Very good question. Why would no? From our analysis here, the integral controller is messing everything up. Is not helping with the frequency response. Is just creating instability and overshoot. So why would we bother with one? Anybody?
Steady state error is 0.
There we go. Steady state error is always 0. The steady state error is always 0. That's the function of the integral gain, is always to eliminate steady state error. Right. So it will be part of a controller. Certainly in practical applications, it will be there. It will always eliminate steady state error regardless of the value of ki, but it will come with the drawback of creating overshoot and creating may create instability. Overshoot then can be compensated for by adding the derivative gain. Moving on to position control, same transfer function, same structure, but now we see that our transfer function here is slightly different. We just took the transfer function we had before. I think we call that S of S. Just integrate that, and this becomes P of S, not theta of S. P of S, which is the position transfer function to voltage. Same controller structure. Now let's go through our system here. What can we conclude? This is proportional controller for position control. It tells us that for high control gains, there is overshoot, even for a proportional controller, and the system also may become unstable. That makes sense because there's a lot of inertia. If you want the mass or motor, just a mass to go from position A to position B, it will jump from, you accelerate with a high control gain, and it can't just stop immediately there. It will overshoot and come back. And so the more gain we give, the more initial acceleration we give to the mass, so it will eventually oscillate. So that's nothing surprising there. And the Nyquist plot attests the same thing. It is a bit hard, but there is a little loop there that it will encircle -1 if it's too high. Proportional derivative controller, look at this. Proportional derivative controller, we have overshoot, but overshoot will appear now for low control gains. So we are coming towards the zeros, and overshoot initially exists. To increase the gain, it will decrease. Here there's a mistake. We have 2 as open loop. Which one is the open loop? Which one is the closed loop? Which one is the open loop? Which one is the closed loop?
Is the black one closed?
The black one is closed. How can you tell? Because the derivative gain added a 0, and this 0 will now cancel the effect of this slope going downwards, and the curve becomes flat. And finally, the PID gain. For the PID gain, for position control, we see the same effect as before. For low gains, it's all good. We start to increase the gain, the system will see oscillations and then eventually become unstable. But it will, in turn, it will, on the other hand, eliminate steady state error in position control. Okay, so just a quick analysis to see how we use them. Now let's take this one step further and see how we implement this PID controller in a discrete version. Let's say you're using an Arduino or something like that. Here is the idea. Now the controller is a discrete function, and because it's a discrete function, instead of S, we use Z to represent a discrete variable. The motor is still a continuous function, it's P of S. If we have a desired position, let's say a desired analog position, we need to discretize that and give that to the motor, to the controller as a discrete position, hence the first analog to digital converter. The microcontroller reads it. It's now a digital signal that it goes to the microcontroller. The microcontroller will process the information and output a signal to the motor, and that output is, let's say, an analog signal, and then it needs to pass through this digital to analog conversion before it is applied to the motor itself. So the motor is a transfer function we used before. This is position control. And now we notice this gate here, that is the sampling gate. This means that it will open and close at every t seconds. T is the sampling time. We are discretizing the input. So in a analog fashion, if we consider the system to be continuous in the way we did in control systems, we can look at the signal that interests us here is the error. That's the input to the controller. This would be at R of Z. We can look at the error, that's the input of the controller. And if you add a continuous signal, this would be it. It would be a continuous curve. However, now we are taking this curve and we are only making observations of this curve at every t seconds. We are discretizing that and looking at the system every t seconds. At t second, I take one measurement to see where the error is. I wait another second. So now at 2t seconds, I will look again on the curve and take another sample, and 3t and so on. So this curve now becomes discretized, and these discrete points have an interval between them, and this is the sampling time t. And now we don't have a continuous signal anymore. We have a discrete version of that signal sampled at a frequency 1/t. Our controller, if it was a continuous controller, would take this form: proportional controller plus the integral over S plus a derivative gain times S. Now we have a discrete version. How can we need to find these three elements in a discrete version? So let's say we are looking at the error at sample K. K is the sample here. K equals to 1 would be T, K equals to 2 would be 2T, K equals to 3, 3T, and so on. If we look at the error at time K, at sample, K, at sample K, what would be the proportional error at that time? Well, the proportional part, let's call that control proportional, would be the error at that instant times Kp. Right? The controller has now three parts: the proportional part, the integral part, and the derivative part. The proportional part at instant K is simply the error times K. What would be the integral gain? How can you calculate the integral gain? How do you calculate the integral of this curve here? Well, the integral of this curve would represent this area, wouldn't it? And if you multiply this area by Ki, that is the integral gain. So if you look at our system at a sample, let's say 3T, right here, what would be the integral gain? It would be this area, would be this area, and it would be that area. Because between T and 0 and T, we are sampling here, and we'll hold that value until the next sample. We now go to T1, we probe here and hold that value until the next one, and so on. This is called a zero order hold function. So the integral gain would be this area plus this area, which is given by, what is the area of one of them? The area of one of these rectangles would be the height, which is, what is the height there? Would be the error at instant K times the base here, which is T. So the error at one of them is like that. If you now want to calculate the error for the entire duration up to a certain sample K, we simply do the sum. All right, so the sample, the error for, let's say 2T would be this plus that. In this equation, it would be the error at 1 times T plus the error at 2 times T. So T comes out of the sum. It's a constant. And this can be implemented easily in a PID controller. You just need to, in an Arduino, you just need to create a variable that stores these values in Arduino. And you could create, for example, an integrator, which is error times K. Integral, let's say a sample I. We have the error at sample I is equal to the error at sample I plus the error at sample I minus 1. Right? It just accumulates the error there, and then you multiply that by T. That would be your integral gain. Now let's look at the derivative gain. The derivative gain is the derivative of the curve itself. In a continuous example, this would simply be the slope of the curve. That's the derivative of the curve. So it would be this slope, that slope, and so on. Here we have a discretized version of it. So we need to approximate this slope. Let's take, for example, this point and this point. We want to calculate the derivative right here. What would be the derivative? It would be this slope, right? That slope there, which is the height divided by the base. What would be the height? Well, the height here would be the error at the instant K minus the error just before that. Let's call that a K minus 1 divided by the shift in time, which is 2T minus T. So this gives the error at K minus the error at K minus 1 divided by the sampling period. Right, this is a very rudimentary application because this signal in reality will be very noisy. It is likely that this will require further processing. So this is the slope at that time. So the derivative gain would simply be Kp times that. Sorry, Kd A times K minus E times K minus 1 divided by T. And now we can add everything up. We add the proportional, the integral, and the derivative portions. Integral is here, times Ki. Derivative is there, times Kd. And the proportional gain is the instant gain at sample I times Kd, Kp. All right. This way, this is how we implement this in a PID controller, in a discrete controller. Any questions? Any questions? No? Any questions? No, there is no questions. There's two options. Either it's all clear, all very good, or it's so confusing that people don't know what to ask. So I hope it is the former. So if it's the latter, let me know, because this is important. Any questions? No? Okay, we'll do an example for this part later. Let's do some exercises then, if there are no questions. This exercise here is similar to control systems. I actually believe I solved it in control systems. So I'll skip this one for now and come back here if there is time. But I'll link the video from control systems in the solution on Canvas. You can look at that here. It's just a PID controller, and you want to find the PI controller. You want to find an appropriate control gain to achieve a certain damping ratio. So let's we will do this if we have time, but let's move on to let's do this one, 68. Let's do this one. So in this example, we have a 24-volt Maxon RE40 DC motor. So this is an actual motor. You can look at Maxon's website. Has the following characteristics, all listed here. Determine the no-load speed, the no-load torque and current, and the voltage and current required to drive a 1 Newton-meter load at 5 radians per second. These are all the parameters that you can find in the data sheet. Torque and speed constants. Resistance, look how small the resistance is, 0.3 ohms. Rotor inertia in the order of 10 to the power of negative 5, the rotor friction constant to the 10 to the power of negative 5. So it's pretty good. All these parameters are really small. Again, if you're looking at the speed, the frequency response, these two will matter the most. So let's do that. So we have all the parameters here, and let's calculate the no load speed and no load torque and current, the voltage and current required to drive a 1 Newton meter, 0.1 Newton meter load at 5 radians per second. Okay. All right. So now let's start with with A is the no load speed. No load speed. What is the no load? What is the equation for the speed? Well, you're looking at steady state response. So in steady state, according to the derivation we had, this would be K M times V. I'm just going to write K because we know the Ki and Km happen to be the same. And if you look at the motor characteristics, they are indeed the same. Minus R, the resistance, times the disturbance torque or the load torque, divided by Ki times Km, which I'm going to write here as K squared, Ki times Km, and they are the same, plus the resistance times the coefficient of viscous friction. So this gives, now for a no load, this is 0. This is no load torque, that is 0. What are we left with? We are left with K times V. K is 32 times 10 to the power of negative 3. V is the nominal voltage, 24 volts. K squared is 32.10 to the power of negative 3 all squared, plus R, 0.3, was it? Yep, 0.3. And B is 10 to the power of negative 5. This gives 750 radians per second, or 7162 rotations per minute. That gives you an idea of how fast the motor spins at no speed. This RE40 is some kind of motor I use in the lab. It has a 40 millimeters diameter. It's quite small. We can see from the specifications and from the speed it reaches that these are indeed very good motors. Okay, so 750 at that. The next question is the no load torque. For now, we're just plugging in numbers, but here we are going to see something else. No load torque. What is the equation for the torque? Torque is Ki times Vb plus Km Td, all divided by K squared plus Rb. Once again, we are dealing with no load, so this term tends to 0, and we are left with K1, 32.10 to the power of negative 3. V is 24 volts, and B is 10 to the power of negative 5, divided by 32 negative 3 squared plus R times B. And this gives approximately 7.5 millinewton meters. 7.5 millinewton meters. This is the no load torque. What is the no load current? I'll divide this by Ki, because it's a torque divided by Ki gives you the current. What is this torque doing? Why is there a torque if there is no load?
Overcoming friction.
Overcoming friction. Exactly, it is overcoming friction. So if it is indeed overcoming friction, then this torque must equate to what?
Omega B.
Omega B. Very good. Omega B. No load speed times coefficient of viscous friction. Does it? Well, the no load speed is 750 radians per second. Coefficient of viscous friction is 10 to the power of -5. And this gives, guess what, 7.5 millinewton meters. Which matches what you calculated here. All right, this torque is here to overcome that friction. What is the no load current? What is the no load current? Is the no load torque divided by
Okay.
K. That's the right Ki. And this is 7.5 times 10 to the power of -3 divided by 32 times 10 to the power of -3, which should give around 0.23 amps. 0.23 amps. So this is to say that when you take the data sheet, all these should be specified. Everything should be specified. But in case it is not, you will see at least the no load current. You will see at least the no load speed. Excuse me. At least the no load speed, from which you can infer everything else. If you know the no load speed, you know the no load current. That's your Ki. Right? It may not be explicitly given in the data sheet, but you can infer from the information that you see for other parameters. Let's calculate the voltage and current required to drive now a 0.1. Plus this C. 0.1 Newton meters at 5 radians per second. What is V? How do we do that? How do we do that? So here we have the input voltage. We want the steady state values. Now we have this load and have this speed. What is the required voltage? Well, we can first look here at this expression and use this expression now because we know omega, we know TD, we can calculate V. So using that equation, let's call this equation 1. So from 1, we can have 5 radians per second equals to 32 times 10 to the power of -3 times V minus 0.3, which is the resistance, divided times TD, which is 0.1, divided by K squared plus RB. I'm just leaving the numbers here to save some time. We can solve for V. This gives V equals to, all these parameters are the same there, gives V as 1.1 volts, very, very small. What is the voltage? And now what is the required current? What is the required current? Well, let's calculate the torque. You may ask, why are we calculating the torque? It's given here. Well, this is the load torque. This torque is the total torque. It includes the effects of friction. So this is from equation 2. From equation 2, we can get the torque as Ki, so 32 times 10 to the power of -3. V is what we calculated here, 1.1 times B, 10 to the power of -5, plus Km, which is 32 times 10 to the power of -3, times the torque, 0.1, all divided by the same thing here, K squared plus RB. And from this, we calculate 0.1 Newton meters. What a surprise is exactly that, right? But it happens to be this because the coefficient of viscous friction is very small, is in the order of 10 to the power of -5. All right, so this torque is the torque that includes the effect of friction. This torque here is the load torque. They are not, they happen to be the same because 10 to the power of -5 is negligible, but if it wasn't, then this torque would be higher than that. So which one should we take into account to calculate the current? The first or the second?
Second.
The second. So the current to drive that load is the torque. Let's call this torque 2. Let's call this torque 1. That's T1. It would be torque 2 divided by Ki, which will be 3.12 amps. Right? This torque accounts for friction and the load. This torque is only the load. Now look at how interesting this is. So here we have a very small torque, very high speed. Very small torque, very high speed. We added a load. Look what happened to the current. How the speed decreased. Right? It went to 5 radians per second, a lot smaller than that. But look what happened to the current. It went from 0.23 to 2.12. Right? So if we slow the motor down, we are making the motor overcome that friction, that a load that we added. Current increases to compensate for that. And another way to see that is that because we slowed down the motor, there is less EMF in the loop. There is more current being generated, or there is more torque being generated as well. Any questions? Are there any questions? No? You guys see the difference between this torque and that torque, right? They are the same numbers, but they don't represent the same thing. Any questions? No? All right, so if there are no questions, let's do exercise 69. I'll have it here as I erase the light board. Take a look at it and see if you have you can develop a strategy to solve it before we solve it together. So that's our curve. And this curve can only be sampled at specific intervals. We'll let the controller run, and then the controller will look at 1 millisecond here, at 0, and we'll take one sample. This sample will be taken here. Let's call this sample the error at time 0. We'll let one time sample elapse, so that is going to be t, and then you're going to take another sample there. So this would be the error 1. And we'll continue with error 2. We'll let another interval pass, and you're going to take the error interval 2. Error at interval 3. Error 3. Then error 4 around here. And error 5 up there. I'm running out of space. Error 5. I sampled at intervals that you see here that are regular and are called t. So these samples that we observed, we can just plug this number 0, 1 millisecond, 2 milliseconds, 3 milliseconds in the curve just to simulate what the microcontroller would see. And that would give us the following values that I'm just going to give here. 0, 0.47, 0.836, 1.805, 3.2, and 5. The question asks, what is the controller output at sample 5? And this is a PID controller. If that is a PID controller, what is the structure we have? We have 3 parts. We have the proportional part plus the integral part plus the derivative part. So let's start with the proportional part. And let's assume that I have gains Kp, Ki, and Kd. What would be the output of our controller for the proportional part at 5 milliseconds? Cp would be the proportional gain times
5.
Times the error at 5, which is 5. So the error at 5, this would be Kp times 5. Now let's look at the derivative gain. What would be the derivative part? It would be KD, derivative KD times the slope at 5. What is the slope at 5? Would be the error at 5, so it would be this distance divided by that distance. That's the slope. So what is the vertical distance? Is the error at 5 minus the error at 4 divided by the horizontal distance, which is the time at 5 minus the time at 4. Actually, I should, to avoid confusion here, I'm going to look small t, it's not capital T. And this is equal to KG times the error 5 minus error 4 divided by T. Error 5 and error 4 are here. T is 1 millisecond. We can solve for this. This would be KG times 1.8 times 10 to the power of 3. Right, A5 is 5. Keep saying A is E5 is 5. E4 is 3.2. The difference divided by 0.01. What is the integral component? What is the integral component?
Is it just
The
the
integral-
sum of all the squares over t?
The sum of all the areas, yeah,
The
over
rectangle, sorry, yeah.
Yeah. So that would be Ki times T times the sum of the error of K when K goes from 0 to 5. Right? So all these areas under the curve. So Ci would be Ki times T, which is 10 to the power of -3, times the sum of all these numbers. I can give you the sum here is 12.5. So this times 12.5. 12.5 times 10 to the power of -3 Ki. What is the final control effort? Well, the final control effort is this Kp plus that. Sorry, is this plus that. Right, and this is the output of your controller. If you're using an H-bridge, then you need to convert this scalar value that you see here, that now depends on, of course, Ki, Kp, and Kd, into a number that goes from 0 to 1 for the duty cycle. You need to map that from 0 to 1. That maps the magnitude, and then you need another signal that depends on now the signal here, the sign of C5, to determine if the rotation in a case of speed control would be clockwise or counterclockwise, or the voltage applied to the motor should be clockwise or counterclockwise. It should be positive or negative, sorry. The duty cycle is related to the magnitude of this output. The direction is related to the sign of this controller output. Okay, any questions?
I have one question.
Yep.
For the integral, you might have explained this before, but how do I explain this? For the integral gain, how come the t term is not inside the summation term? How come it's just outside?
It would be the same. We can write A times T plus B times T plus C times T. That is the same as T times A plus B plus C.
Well, I guess what I mean is, why is it not like the T? Oh, it's because it's a fixed width. I
Yeah,
understand. Thank
yeah,
you.
exactly. If it wasn't fixed, then you're right. Then it would be multiply the respective error. Any other questions? No? Very well. Then we're going to stop here today. Next lecture, we're going to study torque control as an extension of this. If there are no more questions, I'll see you again next Tuesday. Have a great day.